potassium chloride, the rate of solubility increases with increase in temperature. That's why you see it moving like this. Then also in the case of KNO3, that's potassium triazonitrate 5, it also moves with increase, the solubility increases with increase in temperature. But it should be noted that the deductions to be made from this graph is simply that solubilities of potassium triazochlorate 5 and KNO3 increase very rapidly with increase in temperature. So this is potassium triazochlorate 5. So you can see that it can be shown, or it is evident from the diagram, that this one moves with what? The solubility increases with increase in temperature. So as the temperature increases, the solubility increases for this. Then also for KNO3, also follow the same pattern. Then solubility of sodium chloride and calcium hydroxide are independent of temperature, and that is true. You can see that it follows that horizontal line. And also sodium chloride, take note of that, it also follows the horizontal line. That means it is not, the solubility of sodium chloride is not affected by temperature. That is why you see it constant. Then sodium tetraoxosulfate 6 decahydrate. Look at the curve of this. So it goes like this, and when it gets to this edge, it becomes sharp. So what's attributed for this sharpness is because of the fact that when it is heated below 36 degrees Celsius, it is moving here. As soon as it loses this water of crystallization, it comes down, and that is what accounts for this sharp edge. So it shows that at a temperature below 36 degrees Celsius, it is moving normally, it is increasing. Then as soon as it loses the 10 molecules of water, then you have it coming down with a sharp edge this way. Take note of that. Then the application of solubility. Solubility is of importance in pharmacy. It is very important in pharmacy because that is what enables the pharmacist to be able to prescribe the right drugs based on the concentration of interest. The concentration must not be too high and it must not be too low. Then in chemistry, in research, we use this solubility curve to extract essential substances from the raw, such as the plants. So we also use this. Then crystallization, especially the fractional crystallization, where salt with low solubilities crystallizes out first when the solution is saturated. Salt with low solubility crystallizes out first, while leaving those solutes whose solubility is within leaving the solutes whose solubilities is still within the range of the solubility in the solution or in their solution. Then solubility of gases. Solubility of gases is a reverse case to that of the solubility of solids, because in the case of solubility of gases, it decreases with increase in temperature. Then we talk about colloids. We talk about colloids, under which we are going to be talking about true solution, false solution. When it occurs as a true solution, then what it means is that the solid particles are able to dissolve in between the solvents in the correct proportion such that the resulting or the resultant product gives a homogeneous mixture. And when you say a mixture is homogeneous, that is, you have uniformity, you can't discern, you can't distinguish the particles. So they were able to mix, the particles are able to mix with the solvent in such a way that the resultant product gives what? A homogeneous mixture. But when we talk about forced solution, in this situation, reverse is the case. In that situation, the solid particles are unable to mix effectively between the solvents, and at the end of the day, we will be able to observe some particles with our naked eyes. So that is just the major difference. You have homogeneous mixture as the resultant product here, but here you have heterogeneous mixture as the resultant product here. Then let's talk about types of colloids. What are the types of colloids? We have salts and gels, we have the aerosols, and we also have the emulsions. So these are the three types that we have. Under the salts, it is when this solidifies that it becomes gel. So under the salt, we have the dispersed particle here is solid. So solid particles being dispersed in liquid medium. That is what is happening there. But when it has now solidified, then it becomes gels. Then in the case of aerosols, then the examples of salts and gel, we have starch, we have glue, we have agar, we have jelly, we have gelatin, and we have clay. Then under the aerosols, we have liquid or gas being dispersed in the gaseous medium. We have the liquid being dispersed in the gaseous medium. So a typical example of aerosol, we have the fog, and smoke. We also have deodorant from cans, as the aerosol cans. We also have spray of insecticides. Then let's talk about emulsion. We talk about emulsion, we have liquid particle being dispersed in liquid medium. And in this situation, we have the milk, we have the hair cream, we have the cod liver oil emulsion. And it should be noted that the cleaning or the cleansing action of soap and detergent is their ability to form what? Emulsion. The ability to form emulsion. So then this is a table that justifies the solvent or dispersion medium and solid or dispersed substance. So we can use this to summarize what we have been able to discuss earlier. So in this situation, I use we so that I carry you along. So now we have examples of colloids. We have forge. So under this forge, we have the dispersion medium is gas, while the dispersed substance is liquid. Then smoke. The dispersion medium is gas, the dispersed substance is solid. Then we have foam or lather. Then here we have the dispersion medium to be liquid, then dispersed substance to be gas. Then we have emulsion. The dispersion medium is liquid, while the dispersed substance is liquid. Then we have salts. The dispersion medium is liquid and the dispersed substance is solid. So this is a summary of what I explained earlier. Now, these are the UTM questions for solubility. Why I've been able to make it cut it to this level is because most of those questions are repeated. So once you understand a particular one, then you can use that to solve as many questions as possible that are repeated. So this one is talking about question 1. We have a solubility curve For which salt in the graph above does the solubility increase most rapidly with rise in temperature? So having known the concept behind this, so if you look at this very well, we discover that we have salts. Look at calcium sulfate, potassium nitrate, sodium chloride, we have potassium chloride, then we have potassium chlorate. So in this situation, the curve with the which has the steepest is definitely going to be the one that increase most rapidly with rising temperature. So which one would that be? Look at this, from this to this. This one is respond low to temperature. Look at this, from this to this, almost 60 minus 10, that's 50. So you can see that this one has the what? Is the steepest, is the curve with the steepest part. So automatically, the temperature rise is dependent on the steep nature of the curve. And since this one, so as the temperature increases, then we have the steep nature also increases. So this one is the steepest. So automatically, it will definitely be what? Potassium nitrate. So we'll go to our option and see the one with the steepest, which is potassium nitrate. Then the second question is also on solubility, but I think this one has to do with calculation. We have our solubility against our temperature. If the graph above 1 dn cube of a saturated solution of potassium chloride is cooled from 80 degrees Celsius to 30 degrees Celsius, so it's cooled from this range to this range. The mass of the crystal deposited will be, so if you look at this very well, it is cooled from this range to this range. If we trace this to this point, we discover that it will definitely be traced to 4. Then, if you trace this, it's because it's not drawn to scale. So if you trace it to this point, then you will discover that it will be traced to the region of 6. So the first